So now we continue to talk about the algorithms and hardware design to realize the arithmetic operation, which is multiplication. I want to mention there totally has three versions of the multiplication hardware designs. Accordingly, we will have three corresponding algorithms associated with each of these three versions of the multiplication hardware, and we will talk about one after another. The three include the first version, refined version, and the optimized version, or we call the final version. So beginning first with the first version, which is more straightforward, but has a less performance efficiency, and then we will move until the optimized version, okay? So let's see how the first version works. So here has a flow chart. I think this is straightforward. You can see, so basically at beginning from the least significant bit of the multiplier, and then I see whether that least significant bit is 1 or 0. If it's 0, I will do nothing but just shift the multiplicand to the left by 1 bit. If it's 1, I will copy the multiplicand and make sure that the multiplicand is aligned with the position of the corresponding digit of the multiplier. And then I will shift the multiplicand to the left by 1 bit. After that, here is another quite straightforward. I will shift the multiplier to the right by 1 bit, and I will repeat 32 bits. So why I need to shift multiplier to the right by 1 bit? If you look at here, you remember that mathematically what we do is we will first beginning from this multiplier, this digit, and then move to this digit, and then move to this digit, and move to this digit. So this is easy if we're using our eye and our brain. But from the hardware design, it's relatively complicated because you need to make sure the pointer will point to the appropriate location. So instead of doing that, we can use another way, which is still achieve the same result, but with a much less complication, the computational complexity, which is I just shift my multiplier to the right by 1 bit in each time steps. And then same time, my pointer always point to the least significant bits. If I say what I do is, what originally what it mean is I will point to here, right? And then point to here, and then point to here. That is a straightforward way. But because this one has a higher computational complexity, instead we do that, we will we not do this way. Definitely. Let me see. Okay, anyway. So we will not do this way. What we do is our pointer only point the least significant bit. Instead, this, this container, which is register actually, will shift, which can turn the multiplier, will shift to the right by 1 bit at each steps. So in that way, although I only point the least significant bit, actually equivalent to point to this one the first step, point this one the second step, point this one third step. I hope that is straightforward. That is why you can see here, I basically only point to least significant multiplier. And then after I decide whether it's copy or not to do any action, after I shift the multiplicand in order to align with the digit, I only shift the multiplier to the right by 1 bit without shifting this pointer. And then because totally we will implement 32-bit because we do the work on the MIPS 32. Therefore, I need to repeat 32 times. After that, I will finish. So I think let's look at hardware design first, and then we go back to see how this example works. I think that will be more straightforward. Okay. So I don't want to show you the other side, but I want we can think of together. Okay. So let me see. So let's assume if you want to design this, hardware implementation for this first version multiplier, let's see what you really need. I think, and you can pause here, okay, to think by yourself, and then we can start. I think the first thing I need is the register, which used to contain my multiplier. And then I also need another register. Let me just wait 1 second, sorry. Let me just get a new one. So I need one is register, okay, which is contain my multiplier. Oh, sorry, multiplier. Another thing what I need is another register to contain my multiplicand. It is for short, okay, multiplicand. And then what I also need, I need to have some component which enable me to do the addition, right? So that is a arithmetic logic unit. What I also need, I need another container to contain my product. Okay? So what I actually also need, I need something to tell me when I need to do the addition, when I need to do the shift. That is called control unit. We will talk about this in more detail in chapter 4, but here you will know the control unit main idea is more like the brain of the computer hardware to send out the commands. Okay, so then what I do is as the following. I will always take the least significant bit of my multiplier, right? And then this one will tell the controller whether they will need the arithmetic logic unit will do addition or not. Okay, and then my multiplicand always will shift to the left by 1 bit in each iteration, right? My multiplier will shift to the right by 1 bit in each iteration so that I only observe the least significant bit to say whether it is 1 or 0, okay? And then if this one is 1, I will do the summation of or between the register and the product, and then using the results to update the products, right? Otherwise, if this is 0, I will not do this, okay? So basically, this controller will also send a command to the ALU, the arithmetic logic unit, to tell whether you will do addition or other operation. Here is addition. Whether you will do addition or without doing addition, based on here is 1 or 0, right? And then also this controller will tell the multiplicand when you will shift to left by 1 bit, when you will not. And also the controller also will tell this multiplier when you will shift right by 1 bit, when it's not. Okay? Also they will send to the product to decide whether this need to update it with the summation or not. So overall, although it's messy, we will see the slides is much neater, but the idea is the same. So basically, I have the 3 registers which contain the multiplicand, multiplier, and the product. And then the multiplicand will shift to the left by 1 bit in order to achieve that alignment. And the multiplier will shift to the right by 1 bit in order to make sure my pointer do not need to shift, only point the least significant bit. And then we also have the ALU, which is arithmetic logic unit, in order to do the addition when the multiplier is the least significant bit 0. Sorry, is 1. And then I also has another brain of the computer hardware design, which is the control unit, which tell whether your these two registers will shift or not, and whether the product will be updated or not, and when the arithmetic logic unit will do the operation and what operation it will need. Okay, and now if this is clear, I want to ask another question, because we only know what kind of component here is not enough. I need to know how much room I need to leave in order to make sure there's no overflow occurs. So for example, I need to know how many bits this register need to contain, how many bits this two register need to be contained, and how many bits addition this ALU operation need to support. Okay, so assume I try to do is MIPS 32 operation, the addition. Okay, I say one more time. Assume I need to do multiplication in the MIPS 32 hardware. So my question is, how much room or how many bits should be contained by the register for the multiplicand? How many bits need to be contained by the multiplier, and how many bits need to be contained by the products register, and how many bits of the addition need to be supported by ALU? I want you to pause here to think by yourself. Okay, and then continue. So this one, we know if I try to do the multiplication in MIPS 32, the multiplicand and the multiplier, both of them supposed to be 32, right? And the product supposed to be 32 plus 32, which is 64. Therefore, I know the product for sure, I need 64 bits. Okay, so now the question is, how about the register for multiplicand? So okay, let's assume if I only have 32 bits register to contain the multiplicand, whether they are enough. I want you to pause here to think by yourself. The answer is not. The reason is, if I only have 32 bits, when I shift the multiplicand to the left by 1 bit, I will lose the bits, the most significant bits, at each time steps. And those bits are important for the further multiplication or say the addition. Therefore, I need to make sure I have enough room left in front of the register in order to make sure when I do the shift left for the multiplicand register, I will not lose any important bits. Therefore, no matter how many shifts I need to do totally, I need to left the same number of bits in ahead. And because here I will do the MIPS 32 multiplication, in other words, I need to shift the register to the left by 32 type steps, or shift to the register to the left by 32 bits. Therefore, I need to make sure I will left in 32 bits ahead of the room which originally contained the multiplicand. Therefore, the register for containing the multiplicand needs 64 bits. And then I will initialize the multiplicand by putting, say one more time, I need to initialize the multiplicand register by putting the original 32-bit multiplicand to the right half of this register. Say one more time, I need to put or initialize the multiplicand register by putting the original multiplicand, this is 32 bits, to the right half of this register, because I need to make sure when I do the shift to the left, shift to the left, I will not lose any bits. Okay, so now let's think about this multiplier, how many bits you need. So I want you to pause here and to think by yourself, and then continue. So here I need 32 bits. The reason is, all I care for the multiplier is the least significant bit, right? So if you look at here, all I care is these bits, individual bits, right? So when because I will try to do the multiply left to the shift to the left, shift to the right by 1 bit. So that means all I care is the least significant bit. Therefore, I do not vary it, or I do not vary to, maybe lose some important least significant bits when I do shift. Therefore, 32 bits is good enough. Okay, so therefore, I need a 64-bit register to contain the multiplicand and a 32-bit register to contain multiplier. And of course, when I do the addition, I need to make sure my register for containing the product also needs 64 bits. Therefore, my ALU, this arithmetic logic operator, need to make sure to support addition for 64 bits. Okay, so now if you look at back here, it's the same, right? I need a 64-bit arithmetic logic unit. I need a 64-bit register to contain the multiplicand. And I need 32-bit to contain the multiplier. And also I need a 64-bit register to contain the product. So for the initialization, I totally only has 32-bit multiplicand, and then I will initial that by putting that 32-bit multiplicand on the right half of the multiplicand register. The reason is when I do the shift left logic, I will not lose any significant bits, which are important for me to complete the further implementation. And you already initialize the left half, right? So if you look at here, right? So you already initialize the right half of your multiplicand register as the original multiplicand. So how about the left half? Left half, you just put out zeros there. And similarly, you will initialize the product as out zeros. I hope this is clear. And then this one is also you need the control unit, right? Tell when you will do the shift for these two registers, when you will do the addition for this ALU, when you need to update the product, and what kind of operation you need to implement for ALU. Here's addition.